All right, let's begin. Welcome everyone to our first full week of courses, of lectures. Um, Looking forward to it. We've got some uh, exciting material coming up. But first, maybe this is more exciting to you. We need to learn how to actually translate our mathematical models into computer programs. And the first place that we're going to do that is in Excel. So Excel is nice. Excel Solver is nice because you can have all of your data in one spreadsheet, and it's just a nice way to present information and send it to um, other people, clients, colleagues, whatever, in a way that everyone can access and read without having to know Python or C++ or what have you. It's also nice because you can edit data points on the fly and see how the result changes very easily. Um, but it's a little underpowered. It can only use 200 variables, but um, it's very popular for its other benefits. So anyway, I'm going to talk real quick about how to um, access the solver feature in Excel. And these slides are up on the Canvas lecture 4. So first on Windows, and I'll show this again on Windows because I am running on Windows. There's a File tab, Options, Add-ins, and then you're going to click on the Solver add-in, Go, and then check the box, and OK. On Mac, there's a Tools menu on the top row. Select Excel Add-ins. Check the Solver add-in box. If it's not there, the Browse button, and find it. It is supposed to be easy to get from any installation of a modern Excel. Um, so it shouldn't be any more difficult than that. And then once that box is checked and you've pressed OK, a new tab will show up under the Data section. There's this Solver button. Again, I'll do some examples here in a minute, and I'll show you exactly where that is. But before I do any examples, I just wanted to show off several resources if you want other examples of problems. The Easy Excel website has a bunch of them. Frontline Solvers has several of them. These two books they have nice advanced sort of topics tutorials, and this is a good tutorial video, just kind of the intro, showing a lot of the same stuff that I'm going to show today. So on the Open Optimization book that I have linked in the syllabus that my advisor is working on, there are, I believe most of the examples have Excel code tied to them that you can access through the PDF. There's links to them. So that's a good resource as well. They do also have Python, two different types of Python code as well linked there. So if you want to see how some examples can be written in Excel and Python, that's a good place to look. So that's all I have on these slides. I'm going to swap over to my Excel spreadsheet, and I'm going to show you some of the examples that I have written up. Before I do that, does anyone have any questions about how to get Excel or the solver? can show how to get the solver. Sure. Yep. Again, these are. I'm on the wrong window. These slides are posted on Canvas, and you can access them. And you should be able to find these instructions on Google fairly easily. Yeah, I'm not sure if there are any version differences. So that there's a tools menu, or in the file options menu, you're going to go to add-ins, and then click the one you want, solver, and check the box. And there, Windows has a second in-between step. There's a kind of an auxiliary pop-up window that shows up, but I'll show that off here in a second. Great. I'm going to switch over to screen sharing because the resolution is better, and Excel can get a little blurry and hard to read. So let me do that. Is this showing up for everyone? Yes, yes, great. If it's blur or anything, let me know. This should be better than through the webcam. So you may recognize this example from class and from your homework. This is the Soylent varieties problem that we've done. So I've just copied our table of information here and a few other things. I've colored things according to what we're given in the problem, so we want to maximize over this data with these constraints. The variables here I've colored red, and the objective colored golden. So the idea is we want to put a function in all of these unfilled colored spots that will help us express our constraint, or that will embody our constraints. And then we'll go to that proper solver tab up here and put in the constraints there. And I'll show you all how that works. So Excel, if you're not familiar with it, Excel is just a spreadsheet of cells where you can put in values, like I've done here, labels, or functions. So let's start with the total volume function here. Actually, I'm going to correct myself here. I'm going to start by putting in some placeholder values for our decision variables. I'm just going to use 0. Something has... There we go. I'm just going to use 0 here for now. The solver will actually change these values when we implement it. So let's start with the total volume constraint just to show off how this works. So we have our values already written down. To do that, all you do is click on a cell, type the value you want. You do not have to color anything if you don't want to. I think it's nice to look at, but it will not be. It's not important to the function of the solver. You can change the colors in the Home tab or the borders on the cells. So let's start with the total volume constraint. So to write a formula in Excel, you're going to click on the cell you want, and you're going to start with an equal sign. and you can write in either the cell itself or in this function tab up here. So I'm going to write in the function tab, and I'm going to start with sum product is the first command we want. So this is just the dot product of two vectors. Actually, correction, I don't need the sum product. For this constraint, I just need the sum. So if we're doing the total value, or total, let me rewrite this. So if I don't do it capitalized, I can press the tab key, and it will autocomplete. And then I just have to collect the array that I want. So I'm just going to drag over the cells, over my variables in this case, and it's going to input that vector in the function row. And hopefully this isn't too minuscule to see, because I don't think I can blow up the function row at all. I guess it's a little bigger down here in the spreadsheet. Now, in its current state, if I close the parentheses and press enter, it sums all of these. So if I change this to a 1 and enter, it will change this function on the fly, which is nice. If, say I have 1, 2, 3, sure, 63, that's fine. If I do that and I copy this cell and I paste it below it, you'll notice that it's changed the cells that it's looking at. It's actually gone down a cell. If I paste it over here, you'll notice that it is actually looking at these cells over here. So as this is currently written, your reference cells translate with the location of, they're relative to the location of the function. And the neat thing is I can just kind of drag this this square backward to where I want it and press enter, and it's good to go. I'm going to delete these. If, however, I type some $signs in the location between things, or between the h's, or between the indices for our cells, then if I copy it, I can put it wherever I want, and it will keep the same reference cells. So there are times you want to do both of these. Yeah. Ugh. Excuse me. I'm in all kinds of problems. If I select a cell that has a function in it, I can grab this little pip on the bottom corner, and I can drag it, and it will copy that function to whatever cells I drag it over. And if it is not in if it's in the relative format, it will change its reference cells accordingly. So, what else do I want to say about that? Nothing. So total volume, right, is just going to be the cubic centimeters worth of each variant that I want. So we're just summing over the x variables. Total protein is going to be a little different. We're going to click on it, type an equal sign. We're going to use sum product. This is the dot product of two arrays of the same dimension. So what I'm going to do is we're in the proteins, so I'm just going to grab on the proteins column and comma, and then grab on the variables column, and I'm going to press F4, which is going to automatically type in my $signs to make that an absolute reference. So the sum product is just going to be the dot product of this column and this column. And we'll see later that they have to have the same dimension across both dimensions in order for this function to properly run. So we do that, and I can grab this little pip and drag it up, and then I can click on my function row, and this is the calories constraint, so I'm just going to drag our little box over to the calories. And here I'm going to drag this box. I'm going to click back in the function row, drag this box over the fats, and then we're done. And what's nice already, the way I have this set up, we can immediately see that this solution is not actually feasible, because the total calories are the total calories are fine. The total fats are far above 20, and the total volume is far bigger than 30. So we have one more thing to fill in, and that's going to be our objective function. We want the average deliciousness. So again, we're going to use a sum product of the deliciousness and the variables. And you don't need to use your absolute references if you don't understand how they're working. You are just going to have to drag your boxes and resize them as you copy functions if you don't want to use the absolute. And sometimes it's good not to use the absolute if you're copying. We'll see examples of that a little later. So that is not the average. So we want to divide this by whatever our total volume should be to get the average deliciousness per cubic centimeter. Press enter, and now we have our objective function. And I've put in my constraints, I've gone ahead and put my inequality directions just so I have a reminder of how this is going to work. So the next thing I do is bring up the solver, and I need to get a screen capture of that because it's not showing up. Give me a second. Add a new one. Solver. Where is it? It's not showing up as a window. I guess I'll have to do a full screen capture. Do I want? That's gonna get trippy. Give me a moment. I did not think that this would not show up. Alright, I apologize for that. Let's see if this works. Great. Let me zoom back in a little bit. Was not a issue that I foresaw. Great. So, is this showing up appropriately? Anyone? Also make it slightly bigger. Don't know if I can zoom in on this solver window. I can't even blow it up. Huh. I'm not seeing a way to immediately, unfortunately. I can make the spreadsheet bigger. Buzz off. But not the solver. Doesn't look like. I'm sorry about that. Anyway, I'll just have to do it small. Anyway, there's the first box here says set objective, and we're going to click in that, and then click on our objective cell on the spreadsheet. And then we want to maximize, so we're going to click maximize. It's maximum, minimum, and a value of. If you want to find a solution that has a specific value, you can type in that specific value here, click value of, and it will solve it that way. But we want to maximize here. And this third entry box is the variables. So we're just going to click on our variables and drag down to encompass all three variables. And then we have a big box that is our constraints. And we're going to add, press the button that says add next to the constraint box. Again, we have some cells. We have a cell reference for our constraint. We're going to click on the formula side of our constraint. And then that should be a greater than or equal to. So this drop down box has less than or equal to, greater than or equal to, integer, binary, or I forget what the last one is. But you can set all sorts of different variables. So we'll use all of these coming up here. But first we want a greater than or equal to. And the constraint is that it should be greater than or equal to this box. So this box, 4781 at the moment, should be greater than or equal to 1500. That's the constraint we want to add. So we're going to press the add button. We're going to do the same thing, except we want to change the direction of the inequality to less than or equal to, and add. Same idea. Greater than or equal to this time, add. And the total volume should be exactly equal to. We add that constraint, and we press cancel. So here we have that. You can't read this, probably, it's far too small. We have that the cell E (12), so this cell, is greater than or equal to F12. E13 is less than or equal to F13, E14 greater than or equal to F14, E15 equals F15. So that's what's in our constraint row. There's a box below here that says make unconstrained variables non-negative, so that adds our x greater than or equal to 0 as long as that box is checked for all of our variables. And finally, there's a solving method drop-down menu here. We're going to want to click on Simplex LP. So that's the one specifically for solving linear programs. And you just have to make sure that all of your constraints are linear for this one to work. It does have some nonlinear solvers in here that can find local nonlinear optimal values with the GRG, and evolutionary is supposed to find global optimum. But simplex will run fastest, and since we have an LP, that's the one we want to use. And it's the one that we're going to be learning how to do in this class. And then finally, we just press the solve button. I've done something wrong with my objective cell. Yes. So F9. Great, there we go. I guess it was on the wrong one. Solve. And then it spits out, solver has found a solution, all constraints and optimality conditions are satisfied. And it changes our variables and all of our formulas based on those variables. And we're just going to press OK, and it's found our optimal solution. So we want mostly yellow, a little bit of red, and no blue for this iteration of the problem. And we'll come down and look at our constraints. Calories are higher than 1500, fat is exactly 20, protein is greater than 100, and our volume is what it should be. I am not recording over Zoom. I am recording on my side, which may have been a mistake for this particular lecture just because of how the screen sharing works. But thanks for the reminder, regardless. So that's that problem. Does anyone have any questions about what I've done so far? We're covering a lot here, and I know it may not be the most engaging. Just watching me click boxes and change formulas. But this is important material for you all to understand. All right, then we'll move on to a second problem to talk about. This comes from the book. It's talked about in 1.2, I think. I'm not sure off the top of my head. Should have written it down. But anyway, this is the assignment problem from the book. And the book solved it by having a matrix of variables rather than just a vector. So it had, each of our variables had 2 subscripts rather than just 1. So we can do this by having a table of variable locations. And I'm just going to fill in, I'm going to start by filling in some what do you call it? Some placeholder variables. I'm going to get rid of the borders, thank you, because they're distracting. Placeholders here, and what we want to do is use our sum product to enforce these constraints. So our first constraint is that each employee is given a job. So we're going to sum over our employee rows and make sure that they're all assigned a job. So we're going to do this by clicking on the first cell, equal sign, sum product, tab to finish it out, and then our variable row, our data row, and on the data, no, I'm not going to, I want relative for this particular operation. So I'm going to finish it off, and we see that, actually no, this is wrong. I do not want sum product, I just want sum of the employee row. No sum product. But for this operation, I don't want absolute. I want relative, so that, let me change one of these, change some of these variables just so you can see that when I copy it down, it is summing over the correct row. So by this solution, employee 1 was not assigned any jobs. Employee 2 was assigned 1, 3 was 2, 4 was 3. Obviously, this is not a feasible solution for the problem outlined in the book, but this is just a placeholder so you can see how this is working. And because I used the relative format for the range of the sum function, when I copied it down, you notice that you'll notice that the row that it is summing over changed and stayed relative to the cell itself. So similarly, we want to sum over our employees. We want to make sure that each job is also assigned to an employee. So for this, we're going to sum over our job row, our columns. And here, I want to keep the rows, the row index is the same, but not the columns. So I put a $sign before the numbers, but not the letters. Then I finish it off, and I copy and paste, drag it down. I may have to, yeah, I do have to move our box. So I go up and click on the formula and move it to the appropriate column. And I'm being obsessive about the borders. You do not have to. They're not vital to the functioning of the program. And then we have our objective, total number of hours worked. We're going to do this by, now we use our sum product. Here's the magic of sum product. Here's one problem I have with Excel. I pressed enter instead of tab to autofill the function, and it dumped me out of the cell. So tab is the button you want to press. And then I'm just going to grab the whole matrix, and it will pick each element, each corresponding element, multiply them together, and sum over all of that. So we do that. We have 20 hours worked at the moment, and that's everything. So I'm going to pull the solver back up, and we're going to set our objective to our objective cell. L11 is correct. we want to minimize in this case, so I press the minimize button. The variable cells, I grab the whole array, and I add some constraints. So here, all of these should be equal to 1, both of these columns. So I'm just going to grab that, and I'm going to control click and grab a second column. And this will select both of those. I think on Windows it's probably command click. Or on Mac it's probably command click. On Windows it is control. And then I'll press equal sign because I want them to be equal to. And then I just press a 1 in the constraint box. You can put any value you want in the constraint box, or you can assign it a cell. And then I'll press OK. Cell reference box is empty, or contents are not valid. Maybe I can't grab both columns at once. So I'll just try the one column. D11 to D14 equals 1. Let's add another one. The G column equals 1. Okay. Now let's solve this. Let's press the solve simplex LP solver found a solution. All right. So this happened to find an integer solution. We didn't constrain any integer variables in the solver itself, but it happened to find an integer solution, so we're okay with this. But I'm going to show you how to assign integer variables for the sake of it, because your problem may not have the nice structure to allow an immediate integer solution. So back into solver, I'm going to add a constraint. All of these variables should be integer. In the drop-down menu, I'll just press integer. Or even, these should be binary. So I'll just OK that. And that assigns all of our variables to be binary. Solve again. Found a solution. All right. So our minimum is 7 total hours worked. Have I made this sufficiently clear for everyone? Is my explanation good here? Anyone confused? Yes. I'll assume you meant that to my prior question. Great. So I have one more that I want to show off. This also comes from one of the exercises in the book. Feel free to speak up if you want me to go back. So we have two matrices of data, and I've plotted them on this graph. And the problem in the book wants us to find two parallel lines that are a maximal distance apart, that separate these two data points, sets of data, rather. So I'll show you exactly what I mean by that. So we have our variables, again, we have our constraints, and our objective that we want. I'm going to start by filling in some placeholder data in here. And you'll notice that I have this plot set up to take those variable inputs and plot them as lines. You'll see we have parallel lines that are separated, but they don't properly separate the two data sets. So the red line has blue points on either side. Well, both lines have blue points on either side, which is not what we want. We want to have blue points on one side and green points on the other. So we do this by enforcing that our ax minus b is less than or equal to 0, and ax minus the second b is greater than or equal to 0. Well, we want, yeah, so we want ax minus b1, which is our first b, to be less than or equal to 0. That will mean that our line passes above all of our A points in the matrix, all of our A matrix points. And this AB minus B2 is greater than 0, means we want all of our blue points from the B matrix to lie above our lines. And I'm only using B1 and B2 because so there are 4 constraints you could use. You could copy these. Excuse me, Excel. You could copy these, and you could also say B2 here and B1 here. You could enforce these constraints as well. That would be perfectly fine. But they are, in fact, redundant to how this problem is set up. So we don't need them. So the problem in the book wanted us to maximize the distance between the two lines. Now there are some very precise ways to define distance between lines. I have not gone with one of those. I'm just finding the distance between their y-intercepts. So I'm going to do that by equal, just click B1 or B2 minus B1, enter. And then we have our constraints. So here we're going to sum product A, comma, x, and the sum product minus B1. Now I made a mistake here, and that's that our A matrix, or our A vector, and our X vector don't have the same dimension. So what we want to do is include a transpose here, which will flip this vector into a column vector. And that gives our two vectors the same dimension, and the sum product will work and give us -7. And I used relative positioning for this one, but there's one I want to keep constant, and that's the B value, so I just press F4 there to add the $signs in. And then, shut up. And then I drag that little pip all the way down, and we're good. Right? Is that correct? Nope, something's wrong. We do actually want the A vector to be also absolute. So press F4 on that. Oh my lord, what has it done? Drag the pip down. And now we see that all of our green dots are in fact below both of these lines. So our constraints, or our constraint value, is all negative, which is what we want. And we're going to enforce that in the solver shortly. We want a very similar constraint formula for the second set of constraints, so I'm just going to copy it over. I'm going to copy the cell, paste it over, and then drag some of the boxes where I want them. And you'll notice when I drag the boxes, the absolutes, the dollar signs stay where they are. So this new function has some absolute references. Drag the pip down, and just make sure that all of our boxes are where we want them. Great. And we see that this one has some negative values and some positive values. So our constraint here is not satisfied. So the current solution is not feasible. Open up the solver, grab our objective. We want to maximize it. Variables are here. I know for a fact I can control-click to grab two different arrays. It's probably too small to see, but there's our first A value, comma, our B array in the variable cell. So if you have more than one array of variables, you delineate them with a comma in the variable cell. And then we can add our constraints. So our cell reference, we're just going to grab all of these and say those should be less than or equal to 0. Add that. Grab the second column. All of these should actually be greater than or equal to 0. Okay, that's got all of our constraints. Simplex LP. And these do not need to be integer or binary. They're fine being unrestricted. So I solve. Okay, and you'll see that this column is all negative. This column is all positive, which is what we wanted. Can I show this constraints again? Sure. Let me pull it up. Yeah. So in the constraints, I used the array of. I said this array is less than or equal to 0. And let me re-get the objective function. Yeah. So that's probably far too small for most of us to see, but they're there. And these spreadsheets are posted on Canvas already, so when you get the solver installed, the solver should stay intact. I haven't actually tested it, so I'm not positive that it will. I hope it does. I will test that and make sure. Otherwise, I'll send along a text file with the constraints in it. Anyway, so if we look at our plot, we can see that we have two parallel lines that are sort of maximally separated and separate our matrix points. So this comes from the book in a theoretical format, but this is the sort of thing that neural nets do and AI do to sort of train on known data. And then we can use the lines that we've generated to guess about which matrix new incoming data should come in, should be placed into. Obviously, some neural nets are much more advanced than this problem. Many more dimensions. They could have nonlinear separators. But this is sort of a basic and neat, I think, example, primary example of how something like that could work. So those are the three examples that I have prepared. And I will, again, I'll make sure, let me write it down. Make sure solver saves. Yeah, and on the slides I presented earlier that are also on Canvas, there are links to many, many more examples. I advise you all to browse those and see how they've done things. Yeah. So, additionally, I have a few announcements. Obviously, you all found the link on the syllabus to this course. I've changed it to be a password. The link should bypass the password, but that allows me to nix the waiting room in Zoom so that I don't have to constantly tab between my presentation and the Zoom to let you all into the class, and it seems to have worked. A few of you that came early still had the waiting room, but that seems to have been fixed. Tomorrow we'll talk about Python, and I'll show you all how to install Pulp and Spider, and I'll walk you through setting up Anaconda if you haven't done so already. And then how to add the same sorts of what Python program would you recommend to Git? I like Anaconda a lot. There's a link to it in the syllabus near the top, I believe. But it comes with a bunch of other optional packages that you can install. And the IDE, the scripter software that I like to use is Spider. You can use whatever you want. Jupyter Notebooks is really popular. PyCharm is really popular. On that sort of IDE front, but I will be doing all of my presentation work in Spider because that's what I am familiar with. But to reiterate, Anaconda is sort of the overall package that includes your Python installation, your IDEs, and a whole slew of add-on packages for Python. I posted homework 2 yesterday, and I posted the reading quiz for the next reading assignment yesterday. The next reading is very mathematically technical. There are a lot of definitions and a few theorems and proofs. This is important information for going forward, but I don't expect you to know or reproduce the proofs for some of these theorems, for any of these theorems. The theorems, I'm not super happy with how they are presented. Their wording is a little bit confusing, I think, but I encourage you to read it anyway and pick through it and try to figure out what they're actually saying. And I think that the reading quiz helps do that a little bit, and I will certainly help do that in the lecture and in office hours. So don't be disheartened if you're not finding this particular reading easy, because it's on the technical side of things. That is everything I wanted to talk about. So I will stick around for a while and answer any questions anyone has. But other than that, you guys are free to go.
Thank you, Professor.
Thank you for coming.
Is it okay if I ask a question about homework 1 right now instead of doing it during office hours since we have time?
Absolutely. I'll see if anyone has questions on the lecture first.
Yeah, of course.
Well, I'm not hearing from anyone, so go ahead and give me your question.
So for question two, I asked a question earlier about it, and then I think I understood how to set it up, but I'm not 100% on it. So I just wanted to check on that one.
Sure. You post your was your question in Piazza?
Yeah.
Yeah.
And then you
Right.
answered it, but like I'm
Yeah.
just a little bit confused because like the question is different than what like the textbook like shows as an example.
Yeah. 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 Um, did you have a specific issue you wanted to? I've got too many.
Like I think I set up the objective correctly, but then I could only come up with one constraint, and I feel like that's incorrect. I'm not sure.
This was for the shoebox
Yeah.
one? Okay. Right. So there should be more than one constraint. Yes. So there. What what is your current constraint? If you do.
Currently, I just have because I set up. I was like looking through the textbook, and so then there was like another problem that was closer. That was
Mm-hmm.
like a homework problem, so
There
I like
is.
looked through that. Yeah. But it was like a homework problem, so like they didn't have the answer or anything. But I just looked at how it was set up to try to like give me an idea because I was kind of confused by this entire question.
Yeah.
But like I set up like two matrices and then tried to like simulate like what we had from the textbook. And so then the only thing I have is just that the variable is binary.
Okay. So your other constraints should relate to the volume of the shipping packages that they
Right.
have,
Yeah,
right?
that was my original like confusion because I don't understand how you can like do it because it's three separate shipping packages. So I was kind of confused on how
Mm-hmm.
to get them
Mm-hmm.
to sort into that.
Right. So the assignment problem says we're assigning employees to jobs, but we can only assign one employee to one job, and that's it. So that's why it's binary in that problem. Maybe I I don't think I was as clear as I maybe should have been for this for the write up of this problem. But they have as many shoeboxes as they can get their hands on, as they can fit in these packages. So they have access to endless supplies of these shoeboxes.
Yeah.
So, um, but they only have the three shipping packages.
Mm-hmm.
So instead of assigning employees to jobs, what what could we be assigning to what?
You're assigning shoe boxes to containers.
Right, right. Now the difference is that again we have as many shoeboxes as we want as we can fit in these containers.
Yeah.
So instead of being binary, they're really an unbounded integer,
Okay.
right?
Yeah, but like how do you get it so that you're making sure that you're fitting it only in the like 2 cubic feet you have or the 5 cubic feet or the 12 cubic feet?
Well, the shoeboxes have an area or a volume rather assigned to them as well, right? So
Yeah.
if I put two of the small shoeboxes in, that's half a cubic foot.
Yeah.
I'm using up half a cubic foot of whatever package I put it in, right?
Right.
If I put 2 small shoe boxes, I'm using a full cubic foot.
Uh-huh.
Does that
Yeah, that makes
illuminate
sense. I
anything?
just can't seem to like come up with how to make that,
Right.
how to get into a constraint so I can like, so like the problem can be solved.
Right. Okay. Let me think. How would you um, so suppose we only had one of our shipping packages.
Okay.
Just think about only one of them for now.
Yeah.
How would you define the volume of the items we've put in that package?
I would just do like 0.5 times the variable for small and plus 1.2 times the variable for medium, and then plus 3 times the variable for large must be less than or equal to like 2 cubic feet if we're doing the small container.
Right. That makes sense, doesn't it?
Yeah.
Right. So now we have 2 containers.
Yeah.
But our variables are not conducive to more than one container, right?
Okay.
We can't use the same
Yeah.
variables to put shoeboxes in one package as we use to put them in another. Does that make
Right.
sense?
Yeah.
So, how do we fix that? Any thoughts? Remember
I
in the
really.
remember in the assignment problem when we were assigning employees to jobs, we used 2 subscripts on our
Right.
variable, which said
Yeah.
this employee is assigned to this job.
Okay.
Can we do something similar for the shipping problem?
I mean, I just don't know how to do it.
Yeah, it's not maybe obvious. So I'm trying not to hand you the problem, and maybe
I
I'm
know. I
being a
don't want to
little
be
too.
handed the problem.
Yeah,
I'm struggling. I'm sorry. I'm just struggling to like understand how to get it.
yeah. I'm a little. I've been mostly tutoring and TAing where I don't necessarily mind as much giving students the problem more clearly. So I'm struggling a little bit to toe that line. Um, so think about the assignment problem again, and change our employees. Think of our employees as the shoeboxes, and our
Okay.
jobs as the packages.
Okay.
We assign a shoebox to a specific package,
Right.
a certain number of a type of shoebox to a certain package.
Right.
What do our if we're using the 2 subscript scheme from the assignment problem, what do our subscripts, let's say I and j, so x sub ij, what might those represent?
So we could say would be like the shoebox sizes,
Mm-hmm.
and then J is the container sizes that they're assigned to.
Right. And then so how would we think about our small box capacity constraint?
So the small box capacity constraint is 2 cubic feet.
Mm-hmm.
So, um, um, so anything that like where J is S, then you have to be less than 2. I don't.
That makes sense to me.
It makes sense, but like, how do I? I don't want to ask how do I write it because then you're just giving me the answer.
Yeah, yeah, yeah. Just write J equals. Just replace the J with an S for that particular constraint. Does that make
Okay.
sense?
Just yeah. So like, I would just write. Um, so then like I write my variables like I did if it was like one container, but this in this case it would be with the subscripts.
Mm-hmm.
Okay. And then I would include like the sizes of the shoe boxes, like with the thingy. I don't know if that makes sense.
I think so.
Yeah. So I would do like 0.5 times x sub ss plus 1.2 x sub ms plus um 3 times x plus ls must be less than or equal to 2.
Try saying that in words and see if that makes sense to you.
Okay. So the number of containers that fit into the number, sorry, the number of small shoe boxes plus the number of medium shoe boxes plus the number of large shoe boxes that fit into the small shipping container.
Yeah, does that make sense to you?
It does make sense.
Great.
So is that it then? Right? Like
I
that's
can't
how I
tell
can
you.
set up the
I can't tell
constraints?
you that that's
Okay.
right or not.
But am I on the right track to get all the constraints in a way that would allow for the problem to be solved? I
Those
guess.
variables make sense to me. Yeah,
Okay.
but
Okay, thank you.
does anyone else have anything they want to ask? Anything else?
Professor.
Yes.
So, just wanted to make sure when is today's office hours?
4 to 6 Eastern time.
All right. Thank you.
If you need another time, just email me.
I will. Thank you very much.
All right, that's everyone.